Bismillahirrahmanirrahim. Hello everyone, I hope you are all doing well. I welcome you all to the class of real analysis by Walter Rudin. Our discussion is continue on chapter number 3, numerical sequences and series. In today's lecture, we will discuss one of the most important topic of this chapter, that is the subsequences. And further we will discuss an important theorem related to subsequences. The concept of subsequence is almost close to the concept of subset of a given set. You know, a set A is called subset of B if every element of A is an element of B. So in the similar way, we can define a subsequence of a given sequence. So let us discuss how can we define a subsequence. So firstly, if we have a sequence Pn, then the notation used for subsequence is P and K. P and K represent the subsequence of a given sequence Pn. For example, if you write sequence An, then its subsequence will be denoted by A and K. Here the number under A, that is Nk, these are called indices or sometimes suffix. So given a sequence Pn, consider a sequence Nk, that is the sequence of indices, and these Nk are the actually positive integers. Positive integer means set of natural numbers belong to set of natural numbers 1, 2, 3, such that n1 is less than n2, n2 is less than n3, n3 is less than n4. In other words, this sequence of indices is an increasing sequence. Then the sequence Pnk is called subsequence of Pn. This is the simple definition of a subsequence. If Pnk converges, then its limit is called subsequential limit. In more simple words, for a sequence Pn, a subsequence is also a sequence that can be obtained by deleting some terms of the original sequences. So from these lines, you can observe that a subsequence is actually a subset of the sequence. A subsequence can be obtained by deleting some term of original sequences, mean the terms of the subsequence P and K, this set is always a subset of sequence Pn. For example, if we have a sequence Pn is equal to n, this is the sequence of positive integers. So having the terms, when you put n is equal to 1, here the first term is 1. When you put n is equal to 2, the second term is 2. N is equal to 3, third term is 3, and up to so on. We consider its subsequence that just consists on the even number of terms, denoted by 2n. In other words, P and K is the set of even integers. So this P and K consists of the terms 2, 4, 6. So this is the subsequence of Pn is equal to n. So this is the first and simple example of subsequence, and I hope you now you are clear about the concept of subsequences. Next, I have a second example. Suppose we have a sequence 1, 4, 9, 16 up to so on. This is the sequence whose general term is n square. So this is the sequence of square of positive integers, and we choose the indices. Nk is equal to 1, 3, 5, 7. Mean to say, I am taking here first term, third term, fifth term, and seventh term of this sequence. Then the subsequence is, the first term is 1, the third term is 9, fifth term is 25, 49, up to so on. So this is my subsequence. That is, again you can observe that this is a subset of the terms of the sequences. So a subsequence is simply a sequence that can be obtained by just deleting some terms of the given sequences. Next we discuss, this is very important theorem for your final exam. This theorem says a sequence Pn converges to P if and only if every subsequence of Pn converges to P. It is clear that you can form finitely many subsequences of a given sequence. So this theorem says if a sequence Pn converges to P, then its every subsequence also converges to P, and the converse is also true. We suppose your sequence Pn converges to P, and we show that every subsequence of Pn also converges to P. So firstly, we use the definition of convergence of this sequence Pn. By definition of convergence, what is the definition of convergence? We say a sequence converges if for every, this is not for some, this is for every epsilon greater than 0, there exists a positive integer capital N such that the absolute difference of Pn and P is always less than epsilon whenever your n is greater than or equal to n. This is the simple definition of convergence of sequences. I hope this is clear. Because we have assumed that your sequence Pn converges, so it satisfies this inequality. Let Pn, now I have to show our subsequence also converges to P. Our target is to show Pnk also converge to P for some k greater than or equal to k. So for this I will show Pnk minus P should be less than epsilon. So let Pnk be a subsequence of Pn. Then as definition, the sequence of indices satisfy n1 less than n2, n3 less than up to so on. Clearly, after some stages, your nk approaches to infinity, because as I have discussed, this sequence of indices is an increasing sequences. So it is increasing without bound. So nk will be a sufficiently large number that approaches to infinity. Since nk approaches to infinity, so there exists a capital K such that your nk is always greater than or equal to n whenever your k is greater than or equal to k. No matter how large you choose an integer n, because your nk is approaches to infinity. So this is clear that for after some stages, this nk will always greater than your capital N. Thus for k greater than or equal to k, your Pnk minus P less than epsilon. I know these lines are very crucial, and it may be possible that these lines are confusing you. So to elaborate these lines, we understand these lines by using this simple example. Take Pn is equal to 1 over n. Clearly, when your n approaches to infinity, then Pn approaches to 0. It means this sequence Pn is equal to 1 over n converges to 0. So for every epsilon, there exists a positive integer n such that the absolute difference of Pn and 0 is always less than epsilon for all n greater than or equal to n. To specify this example, I choose a specific epsilon, let epsilon is 0.1, and I want to find which n, for which n your 1 over n minus 0 is less than 0.1. I want to find n. When you put Pn is equal to 1 by n, this becomes 1 over n minus 0. What is epsilon? Epsilon is 0.1. Now I want to find which n satisfies this inequality. So this becomes 1 over n less 1 over n minus 0. This is 1 over n less than 0.1. From here we find n greater than 10. So we can choose capital N is equal to 10. That will work here. So this implies when you take your n greater than or equal to n and your n is 10 here, then this inequality is always less than 0.1. So thus Pn minus 0 is always less than 0.1 when your n is greater than 10. Next, we choose a subsequence Pnk. Let its indices nk is given by 2k. Then the indices are, for k is equal to 1, this is 2. For k is equal to 2, this is 4. K is equal to 3, this is 6. K is equal to 4, this is 8. It means I am choosing 2nd, 4th, 6th, 8th and 10th term of the given sequence. As nk is equal to 2k, so when k increases, then nk approaches to infinity. Clearly, when you approach k approaches to infinity here, then your nk approaches to infinity here. So this is the first thing that maybe confuse you, why here nk approaches to infinity. So from this example you can notice that when your k approaches to infinity, then your nk approaches to infinity. Next we show next we want to find a capital K for which nk is greater than or equal to n, for which k this inequality hold. So we need nk greater than or equal to n. What is capital N? We have found capital N is equal to 10 here. This is, so this become nk greater than or equal to 10. So when does this 2k greater than or equal to 10? Because my nk is 2k, so this become 2k greater than or equal to 10. This implies k is greater than or equal to 5. Thus we can choose capital K is equal to 5 here. So if small k is greater than or equal to capital K, then nk is greater than or equal to 10, and we have Pnk minus 0 is always less than 0.1. So in this example we can say that the first thing, your nk is always approaches to infinity. In this case we can find a k that is after some stages. What are the stages? Here after 5 stages. After 5 stages, your nk becomes greater than or equal to 10, greater than or equal to n, and in this case your subsequence always converges to p. Like here, after 5 stages, your nk greater than or equal to 10, and in this case your p and k also approaches to 0 for this epsilon. Further, you can directly evaluate. If you find its second term, this is 1.1 by 2.5. If you find its fourth term, this is 1 by 4, that is 0.25. If you find its eighth term, this is 1 by 8, this is 0.125. So you can notice that whenever you increase n, this sequence approaches to 0. So for all of these terms 2, 4, 6, 8, 10, this your subsequence again approaches to 0. So this is clear from this example that your subsequence always approaches to the same number p as your sequence approach. So this shows that your subsequence is also converges to p. Conversely, we suppose if every subsequence converges to p, then your original sequence pn also converges to p. We prove this by contradiction. We say suppose pn does not converge to p. Our supposition is that every subsequence converges, but we suppose on the contradiction your final original sequence Pn does not converges to P. So then by negation of convergence, when we say a sequence does not converges, it means there exists a or some epsilon greater than 0 such that for every n, whatever n you choose, there exists a small n greater than or equal to n satisfying this inequality, because your sequence does not converges. So in this case, Pn minus P absolute will not less than epsilon. This will be greater than or equal to epsilon naught. Next we construct a subsequence, because we have assumed that every subsequence converges, so I have to need a subsequence. So we construct a subsequence. So we choose integers recursively for n1. Put n1 is equal put n1 here, n is equal to n1 here. This becomes Pn minus 1 P greater than or equal to epsilon naught. When you put n2, this becomes Pn2 minus P greater than or equal to epsilon naught, because here it is given that this inequality holds for every n, for every integer n. So for n1 this inequality hold, for n2 this inequality hold. Continuing this process to obtain a sequence n1 less than n2, n2 less than n3 with Pnk minus P greater than or equal to epsilon naught for all k. Thus we obtain a subsequence Pnk, and so for all Pnk minus P is greater than or equal to epsilon naught. Therefore, now what this definition shows? This definition shows, therefore the sequence cannot converges to P, but the hypothesis state that every subsequence must converge. But this shows that your subsequence Pnk does not converge, because for convergence this should be less than or equal less than epsilon naught. It means, hence we obtain a contradiction. Therefore our assumption was false, and hence my Pn is approaches to P here. So this completes the proof, and I hope now you have a clear understanding about the concept of subsequences and this theorem. So inshallah, in the next lecture we will discuss very important theorem 3.4. So if you find this video helpful, please like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.